Professor Dave and Chegg here. We know about a number of different substitution and elimination reactions and their mechanisms, those being SN1, SN2, E1, E1CB, and E2. But how do we know which of these mechanisms will occur given a particular substrate? Let's go over a few guidelines that will help you decide.
When we are considering a situation where one of these reactions will occur, we will be given some reagents. There will be a substrate, and there will be some kind of base or nucleophile. We may also have other information, like the solvent in which the reaction is being run, and perhaps the temperature. First, let's look at the substrate. To keep things simple, let's use some simple alkyl halides. Let's say we have a tertiary substrate. That means the carbon that bears the halogen is connected to 3 other carbons. From this we can discern only one thing, that SN2 will be impossible. Remember that SN2 must occur via a backside attack, so the nucleophile must approach at a 180-degree angle with respect to the carbon-halogen bond. But with a tertiary substrate, there is too much alkyl in the way. A nucleophile just will not be able to approach, so SN2 is impossible. However, E2 is possible because all of these beta protons are accessible, and both SN1 and E1 are possible because if this leaving group leaves, it will generate a tertiary carbocation, which is stable enough to form. So a tertiary substrate will only negate one of the possible mechanisms. On the other hand, if we have a primary substrate, all of a sudden SN1 and E1 don't look so feasible. It will be very difficult for this leaving group to leave, as that would form a primary carbocation. As we learned, these are quite unstable, so these two mechanisms typically will not occur on primary substrates. SN2 and E2 are both prime candidates, however. And with the secondary substrate, there isn't really any valuable information we can get, and all mechanisms remain possible. Finally, we want to include E1CB and state that this will be possible for any type of substrate provided that the leaving group is 2 carbons away from a carbonyl group. Next, since we just talked about the substrate, let's talk about the base or nucleophile, which are words that describe similar features, in that any nucleophile can act as a base, since whatever excess electron density would coordinate to a carbon atom can also extract a proton. In fact, nucleophilicity parallels basicity, but there are certain factors that make a molecule better suited for one task over the other. First, we must realize that strength is a factor. Take something like hydroxide. This is unstable and therefore reactive. It is a good nucleophile and a strong base. Because of this, it does not need to wait for a carbocation to form. It will tend to react with some substrate when it collides. For this reason, hydroxide will tend to do SN2 or E2. We can ignore SN1 and E1 as possibilities. Conversely, the conjugate acid of hydroxide, water, is not very basic. It is a weak base and a poor nucleophile. It is stable and not reactive enough to do SN2 or E2 in the presence of a substrate, but if a carbocation forms, then it can do SN1 or E1. So in either case, we can disregard 2 of the mechanisms based on strength. We should also be aware of steric hindrance associated with the base or nucleophile. The bulkier the base, the less likely it is able to act as a nucleophile and coordinate to the molecule. Something like tert butoxide, which just like any of the alkoxides or hydroxide, is strong. We know this because of the formal negative charge on the oxygen. Since it is strong, we know it will do SN2 or E2, but because of this tert butyl group, it is way too bulky to actually coordinate to the substrate and do SN2. Because of this, tert butoxide is the classic E2 promoter. It is much easier for it to approach the edge of the molecule, extract a proton, and be on its way. Similarly, the weak analog would be the conjugate acid tert butanol. As this is weak, we should consider SN1 or E1, and again, due to sterics, SN1 is not likely, and we can conclude E1. So we can see that looking at both strength and sterics of a base can sometimes be enough to determine the mechanism, although if the base is sterically unhindered, we can't get much information. Next, we should consider leaving group ability. If we examine just the halogens, the larger the halide ion, the more stable it is, so leaving group ability increases going down the group. The better the leaving group, the more likely it is to leave, and the more feasible carbocation intermediates will be, such as with SN1 or E1. We should point out that this is the case in aprotic solvents, where the halide ion can't participate in hydrogen bonds, whereas in polar protic solvents, the leaving group ability trend will reverse, since smaller ions will spend more time interacting with protons in solution, which stabilizes them. By the same token, smaller halides are less stable and more reactive, and thus better nucleophiles in aprotic solvents. But in polar protic solvents, they will be tied up interacting with solvent, and thus the nucleophilicity trend for the halide ions will also reverse. This is just something to be aware of. Finally, we do want to understand how temperature can be a factor in influencing the mechanism. Let's say we have this secondary alkyl halide and hydroxide. The substrate isn't telling us much. The sterics on the base doesn't give us anything either. Hydroxide is strong, so we know it's SN2 or E2. As it happens, if we run this at a pretty cold temperature, let's say 0 Celsius, we are much more likely to get the SN2 product. If we run this at a hot temperature, say 100 Celsius, we are much more likely to get the E2 product. To understand why, we have to recall this equation. This is the Gibbs free energy equation, and it states that the change in Gibbs free energy depends on the change in enthalpy minus temperature times the change in entropy. Recall that if delta G is negative, the reaction is spontaneous, and if it is positive, the reaction is non-spontaneous. Well, looking at delta S, we know that entropy is a measure of the dispersal of matter and energy. With the substitution, we are just swapping one group for another, so it is not particularly entropically favorable or unfavorable. But with elimination, we have a substrate and a base, which are two things, and we end up with the conjugate acid of the base, the alkene product, and the leaving group, which are three things. This represents an increase in the dispersal of matter, and is therefore entropically favorable. Notice that the change in entropy is multiplied by temperature in this equation. This means that if we have an entropically favorable reaction, like an elimination, which means a positive delta S, the higher the temperature is, the more positive this term will become, and the more likely it is that delta G will be negative. So elimination reactions become more spontaneous at higher temperatures. Whether we remember this explanation or not, it will suffice to simply remember that higher temperatures favor elimination, whether E1 or E2, and lower temperatures favor substitution, whether SN1 or SN2.
So we just went over a few factors that influence which reaction mechanism will occur. These were the degree of substitution on the substrate, the strength of the base or nucleophile, the steric hindrance associated with the base or nucleophile, the leaving group ability, and the temperature. Professor Dave for Chegg. See you next time.